Hey, so this is story number 26, where we are supposed to research a couple of boosting models to use on our crop data. So during the process of this story, we first needed to actually figure out what boosting is and how to use it, and it's kind of a simple concept. It's just taking a bunch of weak learners or regressors that only slightly correlate with the ground truth and combining all of these regressors to make a strong regressor that correlates closely with the ground truth. There are two separate AdaBoost models that we make in this story. So one is AdaBoost and the other is XGBoost. And the two are not all that different from each other. They differ slightly in the implementation of that same idea. AdaBoost uses decision stumps for its weak learners, which basically just means it's a decision tree with a depth of 1. And XGBoost does not have that restriction, and it works in a similar way. XGBoost is a subclassification of a larger group of algorithms called gradient boost. And this is the implementation for XGBoost. And during this implementation, we first have to normalize the yield, so it always occurs between 0 and 1. And the reason we do this is not for this model specifically, it's just to maintain consistency with the other models. And both XGBoost and AdaBoost have two hyperparameters that go into it. The number of estimators, which is just the number of weak learners we're using in the classification, and the learning rate. And while we're running this piece of code, I take a bunch of possible number of estimators and possible learning rates. I take the Cartesian product between them and try every possible combination of number of estimators and learning rates. And that's XGBoost. The code for AdaBoost is very similar, only this line here changes really. Everything else is almost exactly the same. The output is a little bit easier to see here than it is for XGBoost, but here's the output. This is the number of estimators for this particular iteration of the loop. This is the learning rate for that iteration of the loop, and this is the coefficient of determination for that particular model, which basically gives us, which is a performance metric for the model. And as you can see, none of these are quite working very well. And a coefficient of determination that is negative indicates that the model is basically useless, because our baseline for a good regressive model is a coefficient of determination of 0. Achieving a coefficient of determination of 0 would basically mean that we're just predicting the average value of the training data. And that's it.